Hello students, today we are going to discuss about the characteristics of unijunction transistor. The characteristics of the unijunction transistor is drawn between the VE and IE, where VE is the voltage in the emitter section and IE is the current from the emitter to the base section. So if you see the construction of the UJT, here you can see that this is my VE, where this emitter portion is considered as a diode. This is PN junction diode here. This portion is considered as a diode here. And these two are the internal resistances of the UJT, which is RB2 and RB1. Now this RB1 varies, as we know. When we have discussed about the construction of the UJT, we have seen that RB1 varies due to the current flowing through it, and IE is the current that is flowing in this. So the characteristics curve is drawn between the VE and IE. To understand the characteristics curve, let us first start with the voltage at the emitter at which the IE equal to 0. So this is the voltage, let it be VE dash. So at this particular voltage, the current here is 0. Current here is 0. Now if you decrease this voltage VE dash, then you notice that we get a current in the opposite direction. That means if you decrease the voltage below VE dash, this diode become reverse biased and you are getting a reverse saturation current which is flowing like this. So this RB2. So if you decrease the voltage below VE dash, we are getting a reverse saturation current, and if you decrease VE dash further and make it 0, I will get the maximum reverse saturation current, which is I call as IEO. So IEO is the reverse saturation current. It's the reverse saturation current, and this the value of this reverse saturation current is maximum whenever this VE dash is equal to 0. Now to make the diode forward biased, I have to increase the value of this VE such that this VE will be greater than the two voltages VD plus eta VD. So that means this diode will become forward bias if the applied voltage VE, that means the voltage at the emitter junction, is greater than this plus this one. So from here, this is the voltage VE dash. At this particular voltage VE dash, the current IE equal to 0. So that means the diode is still reverse biased. If we increase the voltage little bit above this VE dash, then the diode start conducting little bit. It just start conducting little bit. So if it start conducting, then I will get a current which is increased linearly. So this is the portion where you are increasing the value of this VE dash and the diode is just start conducting the current. So you are getting some current here, I, which is increasing linearly with the increase in the VE. So if you increase further, if you increase the value of this VE dash further, then this VE dash will be equal to or greater than this VD plus eta VB. So V dash will be greater than or equal to VBB. So if we consider that at this point, at this voltage, which I call as an VP, at this voltage, the value VP is just equal to VD plus eta VBB, and we call that as a peak voltage. So Vp is the peak voltage at which it is equal to Vd plus eta VBB. You notice here that before reaching this VPP, that means before reaching the peak voltage, this diode start conducting. And you are getting a small amount of current. Though it is less than Vd plus eta VBB, still the diode conducts and it gives rise to a small amount of current. Actually, you can say that the diode will start conduct after the voltage V dash, and if you increase it further up to Vp, then the diode will conduct fully. I can say that the diode will conduct fully at the voltage Vp, which is equal to Vd plus eta Vb. So I can say that the diode will conduct fully whenever the voltage across this emitter junction is equal to Vp, which is nothing but Vd plus eta Vb. Now what happens if you try to increase the voltage beyond Vp? So if I try to increase the voltage beyond Vp, that means if I increase the voltage Vp beyond this, if I increase the voltage Vp beyond this, then the diode will conduct fully and the majority carriers will start conducting in this path from emitter to the base one. Now here, this is N substrate. As you can see, this is the N substrate here. So the electrons, majority carriers here will be electrons. So electrons will move in this direction and holes will be coming into the UJT. So holes will now start injecting here. So as we increase the voltage Vp greater than this Vd plus eta VBB, the holes start injecting into the UJT. So because of the injection of the holes, that means because of the movement of the holes and the electrons in the opposite direction, the conductivity of this portion will increase. That means there will be a rise of current. So the current will now rise. Current will increase. Current will rise. Current start rising. Now if current start rising because of the induction or because of the injection of the holes, so because of the movement of the carriers, majority carriers, conduction will be increasing. So as conduction increases, the internal resistance RB1 will start decrease. That means the resistance which was initially RB1 before any injection of the carriers, majority carriers, now after the injection of the majority carriers, the resistance of this portion will now decrease as the conductivity increases. So as resistance RB1 decreases, this eta value will also decrease, because we know that eta is nothing but RB1 divided by RB2 plus RB1. So as eta value decreases, this eta VBB, that means this V1 will also decrease. So that means initially this emitter junction is opposed by V1. Now the opposition that this emitter junction portion will get will be less, because now V1 is less. But on the other hand, current is increasing. So as current increases, V1 decreases. So what I can say? I can say that to maintain this current, the amount of emitter voltage that is required now will be less. Okay, so this voltage required will be less because now this V1 is less. So the less voltage is required to overcome this V1. So as IE increases, this voltage across the emitter and the base one, which is VE, decreases. So that is why as current increases, your voltage VE decreases, and it decreases up to a voltage which I can call as VV, called valley voltage. Valley voltage. Now, once it reaches this point, which we are calling as a valley, because it looks like a valley here. This is a hill. This is going again up. So this is a valley. So this is a valley voltage. At this valley voltage, the current becomes saturated, and I call it as an IV, which is called valley current. The current due to the majority carriers saturated. The currents due to the majority carriers saturated. So there will be saturation of the current here after the valley voltage. After reaching this valley voltage, that means after reaching IV, if you want to now again want to increase the current, for that purpose, what we have to do, you have to apply again more VE. So you have to apply more VE, because now you are in the saturation region. That means your current is now saturated. Once it is saturated, after that, if you want to increase the current, you have to increase the voltage in the input section. So now this portion behaves as a linear portion where VE is directly proportional to your IE. So here VE is directly proportional to IE. So we are getting three parts here. We are getting three parts. This portion up to this, we call it as an cutoff. Actually, it is cutoff up to this, but we are considering the cutoff region up to this because after this the current start rising very fast. So we can call, or you can take this portion as an cutoff. Though it is not actually cutoff, we can consider this to be cutoff because after this point only the current increases very rapidly. Now this is a very interesting part. If you see this part, what you can see here, we can see that with current voltage decreases, and we call it as a negative resistance region. It is negative resistance region because here in this portion, if you see, if current increases, voltage decreases, and after this point, your current is now saturated, so we call it as an saturation region. So once the UJT becomes saturated, then after that, if you want to increase the current, then you have to apply more voltages. You have to apply more voltages here. So initially, to overcome this V1, I have to apply a voltage Vp. So once I overcome that voltage V1, if I overcome this voltage V1, then this diode will fire, and as this diode fires, current start flowing, or the majority carriers start injecting into the UJT, and the internal resistance of the UJT RB1 decreases as the conductivity increases, and because of that fact, V1 decreases, and to maintain that IE current, the voltage required will be less, which is this portion. So this is the portion. Here what is happening? Holes are injecting to the UJT and electrons are moving out from the UJT. So after that, we are getting the saturation. Is the saturation, the current will be saturated. Once the current is saturated, after that, if you want to increase the current, you have to apply more voltages. This is basically the characteristics curve of a UJT. So the UJT will remain cut off up to this Vp, where Vp is the voltage that is required to overcome the voltage drop, this one. Now if you see the value of eta generally lies from 0.5 to 0.8, and if you are applying VBB 10 volts, then the V1 will be equal to 5 volt. So how much VE will be required to inject the holes into the UJT? The voltage required will be more than 5 volt in this case. If you take this example, for this example, the VE required so that the holes will be injected inside the UJT will be greater than this 5 volt. So that is why we are having Vp at the higher value here, Vp at the higher value of VE. Now if we give voltage greater than this 5 volt, then it will start conducting, so its resistance will decrease, so eta will decrease, and similarly this V1 will decrease, and to maintain that, what I have to do? I have to also decrease the value. So this VE will also decrease as your IE will increase. Now this negative resistance region here in this case of UJT have lots of application. So one of the application is that we can use this negative resistance region of the UJT to construct an relaxation oscillator, or to construct or develop a sawtooth wave. So UJT can be used as an sawtooth wave generator, and that because of this negative resistance region.